Recording. And now I request Ms. Hafsa to begin the formal introduction of the webinar.
All right. Good afternoon, everyone, and welcome to another session of Science Chronicles. This series aims to explore the history and development of scientific ideas, bringing together experts to share their insights with us. We're excited to have you all here for what is going to be a thought-provoking session. This webinar is organized by IPKI in collaboration with EcoSF. The EcoScience Foundation is a specialized agency of the Economic Cooperation Organization, an intergovernmental entity with 10 member states, including Afghanistan, Azerbaijan, Iran, Kazakhstan, Kyrgyzstan, Pakistan, Tajikistan, Turkey, Turkmenistan, and Uzbekistan, mandated to promote science, technology, and innovation amongst the ECO member countries. IPKI is an organization committed to making the world a better place by promoting science education, fostering intellectual curiosity, and bridging gaps in access to quality learning opportunities. Today's session delves into one of the greatest mysteries of modern physics, dark matter. And to guide us through this fascinating topic, we have with us Dr. Muhammad Rehman, an assistant professor of physics at ComStats University, Islamabad. He earned his PhD from the University of Cantabria, Spain, and has 8 years of experience in teaching and research. His work focuses on supersymmetric models, Higgs decays, dark matter, and collider physics, bridging theoretical predictions with experimental data. Beyond academia, Dr. Rehman is dedicated to science communication, making complex physics concepts accessible to everyone. And today he will guide us through the mysteries of dark matter, its evidence, ongoing searches, and the role of theoretical models in understanding this cosmic puzzle. Without further ado, let's welcome Dr. Rehman.
Thanks, Absa, for a nice introduction. So I think I'll start straight away. So as she explained, our today's topic is the dark matter. It is said that the path to the understanding and learning, it starts with asking questions. So it doesn't start with what we already know, but what we don't know. So in today's era, there are some biggest questions that as a particle physicist or as a physicist that we want to answer. And dark matter is one among them. And then there is dark energy and how this universe came into being. Are there extra dimensions? Why there are four forces of nature? So all these kind of questions, these are the big questions, and answer to any one of them can lead you to the Nobel Prize. So in this talk, our main focus will be on the dark matter. What is this dark matter? How do we know why there should be dark matter? And how we can explain the existence of dark matter. But during this journey, we also need to know about our present understanding of the universe, how this universe is made up, and how we can explain the things that we see around us. So if we start our journey, I'll start with a very simple explanation. So for example, if we want to look at the matter, the scale of the matter is 10 raised to power minus 2 meter. So if we zoom this, we will reach up to molecule level, which is 10 raised to power minus 9 meter. I'm not sure my pointer is visible.
Yes, it is visible, sir.
Okay, thank you. So at the molecule level, the size of the molecule is 10 raised to power minus 9 meter. And this is the scale where all this nanosciences and chemistry works. If we zoom this further, we will reach at the level of an atom, which is 10 raised to power minus 10 meters. And this is the scale of the atomic physics. And this is still not the end. We can zoom it further, and then we will reach at the nucleus level. And this is the 10 raised to power minus 15 meter or so. And inside the nucleus, we know we have protons and neutrons. There was a time when these particles, they were considered as a fundamental particles, but now we know they are not fundamental anymore. And these particles, they are made up of quarks. So even zooming further, we will have 6 quarks. and 6 leptons. Uh, and electron, for example, is a kind of lepton. So this is a simplified, a brief introduction of the particles that we already know. So there are, if we talk about the fundamental particles, we have 6 quarks that are top, bottom, charm, strange, up and down. And similarly, we have 6 leptons. And these are the fundamental particles that make up all the stuff around us that we can see. But as I said earlier, that's not everything to it. This is just 3 or 4% of the total stuff that exists in the universe. And the biggest question is what this other stuff is. So in this talk, we will see what this other stuff is. But before that, I'll briefly explain the present contents. So as I said, we have 6 quarks, 6 leptons, and these quarks and leptons, they interact via gauge bosons. And for the gauge bosons, we have photon, we have W plus minus, we have Z boson, and then we have gluons. These are the force carriers through which these fundamental particles, quarks and leptons, interact. And then there is another very important particle that is called Higgs boson. And this particle is responsible for giving masses to the fundamental bosons and quarks and leptons. So this is the current particle contents of the universe. And even from these particles, for example, like top and bottom quark and this tau and mu, these are the heavier particles and they are not stable. All these particles, they decay into these lighter particles like up quark, down quark, electron, and the all the matter stuff that we see around us, the stars, the galaxies, and all these are made up of these 3 particles: the up quark, the down quark, and the electron. And then we have these neutrinos. So whole matter contents of the universe, they are made up of these 4 fundamental particles. Uh, and now let's talk about how these fundamental particles interact. So there are, of course, 4 fundamental forces. One is the gravity, you have all heard of. And then we have the strong interactions, electromagnetic interactions, and weak interactions. Yeah, I'll not go into detail why we need strong interactions and what are the electromagnetic interactions. I hope every one of you may have studied physics, so these kind of interactions are already obvious. Anyway, so the theory that combines all these interactions into a one unified framework is called Standard Model. So there we have the quantum chromodynamics, that is the study a branch of physics that deals with these strong interactions. And then we have the electroweak theory that was developed by Glashow, Weinberg, and Salam. Um, and then these 2 theories, they are combined into a bigger framework that is called Standard Model. So this is the present understanding and the best model that we have developed so far. And many Nobel prizes were awarded in the development of Standard Model. For example, the quantum chromodynamics, this is the sub part of a Standard Model. It was developed by this mainly by these 3 scientists, Julian Schwinger and Richard Feynman and Tomoga. They all played a very active role in the development of quantum electrodynamics, and they were awarded Nobel Prize for that. Similarly, the electroweak interactions, the theory was developed by the 3 greatest scientists, Sheldon Glashow, Abdus Salam, and Steven Weinberg. They developed this theory in 1960s, and it was a wonderful time. Many advancements were made during this time. For example, in 1961, Glashow proposed a SU2 cross U1 structure of the Standard Model, and building on that, in 1964, Dr. Abdus Salam proposed the 4 gas bosons for this structure and developed that. And then in the end, Steven Weinberg used the idea of Higgs mechanism to incorporate all those advances into a one unified theory. So this was a very beautiful work that led to the development of standard model. And then another great achievement came from the development of quantum chromodynamics. These three scientists, they developed the idea of asymptotic freedom, and then they were awarded the Nobel Prize in the 2004. So this was a brief introduction of the standard model. I did not go into many technicalities here because I think our main focus is on the dark matter. So I'll jump right away. So even though standard model is a very beautiful theory and it has withstood thousands of experimental just verifications, and it has beautifully predicted many phenomena that have been tested again and again at the experiments. But as uh, it goes with all the theories, standard model is not a final word. So there are some problems that tell us that there should be some physics beyond the standard model. For example, when we calculate the Higgs boson mass in the standard model, this mass is not finite. Standard model predicts that the Higgs boson mass should be divergent, should be infinite. But we know in experiment we have measured the mass of the Higgs boson and that is finite. So this is one problem in the standard model that we need to take care of. And then, of course, there is this dark matter problem that we will be dealing with in detail in the next slides. There is another problem in the standard model that says that the neutrinos standard model uh, assumes neutrinos are massless, but in the experiment we see neutrinos have masses and they mix among each other. So this is another problem in the standard model that tells us we need to go beyond the standard model. So due to these problems, we need to look forward for new theories. And now let's look at in detail what is the problem of dark matter. So, have you ever wondered if there is a mutual attraction between the sun and earth, then why doesn't earth fall into the sun? Of course, you know, uh, there is this mutual attraction, but the earth's velocity, orbital velocity, is so high that it rotates around the sun. So if you look at this, if these equations bother you, you can skip these equations, but this is just a metric level stuff. So I hope most of you will be able to follow. So you see, according to Newton's gravitation law, the force of attraction is equal to the Newton's gravitation constant, and then the mass of the sun multiplied by the mass of the earth. And this is inversely proportional to the square of the distance between them. So this force of attraction is compensated by the centripetal force, which is equal to the mass of the earth multiplied by the velocity square and divided by the distance. So if we equate these two forces, we get this very beautiful relation. V is equal to gm over r square root. So this is very important relationship, and if you understand this relation, you will be able to follow the discussion very easily. So you should try to focus on this relation. Here, what this relation tells us, if you increase the distance, the orbital speed should decrease. You see, this is the inverse relationship between the uh, distance and the orbital speed. And this is what we observe when we look at the solar system. For example, Mercury is the nearest planet to the sun. So its orbital velocity, if you look at in this table, is 47.36 kilometer per second. And its distance from the sun is almost 58 million kilometer. So the next planet is Venus, and there its distance is 108.21 million kilometer. But as the distance is increased, its orbital velocity is decreased to 35.02. And now you can look at all these planets. So as long as you go along the furthest from the sun, for example, for the Earth, we have the distance 150 million kilometers, and the orbital speed of the Earth it decreases to 29.78 kilometers per second. So with increasing distance, the orbital speed decreases, and this is what we expect from the Newton's laws. And this is the relation that we were seeing. So if we just increase the distance, the orbital speed should decrease. Now, this is the same thing that we would expect to hold at every stage. But when we look at the spiral galaxies, here we would expect the same. Uh, for example, this is the center of the galaxy, and we would expect that the stars near to the center, they will be having the orbital speed very high compared to the stars that are at the further edges of the galaxy. For example, some star here or some star here. So what we expect is this kind of behavior that you can see in this blue line in the plot that is uh, here. So this expected behavior is, if we increase the distance from the center, the orbital speed should decrease. But what happens when we measure this distance for these parallel galaxies? The thing that we see is that this distance remains almost constant. This distance does not decrease. And this is the strange behavior that we want to understand why this is happening. Because from our past experience, we were saying that if the distance increases, the orbital speed should decrease. But for the case of spiral galaxies, we see this discrepancy that the distance remains constant. So can you tell me how we can explain this discrepancy? The answer lies in this expression that we obtained few slides earlier. So again, here we can see in this expression, if this velocity remains constant, what else can be done if we want to increase the distance? So here in this expression, g is constant. We cannot change the value of g. But what we can do, we can assume that there is some more mass that is compensating the radius or the distance, and then this increase in distance is compensated by increase in mass, and this velocity remains constant. So this is what happens, and this is the first evidence that led to the existence of dark matter. So when we were expecting the radial velocity, orbital speed to decrease, but we saw the uh, constant speed, we proposed that there must be some dark matter there, some non-luminous matter that we are not able to see, that is causing this orbital speed to remain constant. And this was the first evidence for the dark matter. And then there is this is not the only evidence. There are other evidences also. For example, we have this very beautiful phenomena that is called gravitational lensing. What happens is that when we have some mass, uh, that mass causes the space-time around it to curve. And due to this curvature, if there is some light coming from some source, that light will follow a curved space-time path. And due to that, the observer will not see that object at that place, but it will see that object at displaced points. For example, if the source lies here, then due to space-time curvature, the this object will be visible at these two places. And these are this is the explanation of the gravitational lensing. So if there is some mass, it will cause curvature of the space-time, and due to this curvature, we will see multiple objects for the same source. And this phenomena uh, also leads to the existence of dark matter For example, what we are seeing in nature is that we are seeing these gravitational lensing objects, but we don't see any mass that could cause this gravitational lensing. So the question arises, if there is no mass here, why we are seeing this phenomena of gravitational lensing? And the explanation is obvious, as you can guess. This lensing is caused due to the existence of some non-luminous matter that we now call the dark matter. So even though we cannot see matter here, but this matter is acting as a lens for the gravitational lensing, and we see these kind of objects. So this is another strong evidence for the existence of dark matter, and that tells us that there should be some non-luminous matter that we cannot see using our ordinary telescopes and other devices, and we need to explain this existence of dark matter. So keeping these evidences in mind, we have we have conducted some experiments to measure how much amount of dark matter could be present in the universe. For example, the image that you are seeing is taken from the Planck's experiment. This is a space observatory that have mapped our universe and has provided us with the current estimate of the total energy density of the universe. And in this total energy density, the result tells us that the 71% of the total energy density consists of the dark energy, and then almost 29% consists of dark matter and the visible matter. So when there is this uh, there is this quantity that we call dark matter relic density, and we denote it by the mega h square. So the Planck experiments tells us that the dark matter relic density should be equal to this value. And now in the future slides, we will try to see how we can obtain this dark matter relic density and how we can explain the existence of dark matter. Moving on, now we have established that there are many evidences of dark matter, and we need to understand how those uh, explanations could be, how this issue can be explained, and what is dark matter. So there are different proposals. For example, one proposal says that there is no dark matter, but we need to modify the Newton laws. So you see, the existence of dark matter was proposed on the basis of these rotation galaxies, where we did not see the expected curve, but the flat rotation curves. So one option to explain this flat rotation curve could be to propose that the Newton laws should be modified. In the next slide, we will see what is this modified Newtonian dynamics. Another approach is the primordial black holes. They can also explain the existence of dark matter. And then we have axions, sterile neutrinos, and then finally weakly interacting massive particles. So now let's look at them one by one. Talking about the modified Newtonian dynamics, these are, as I said earlier, proposed as an alternative to dark matter. And this theory is called the MOND, which is modified Newtonian dynamics. And it says that there is no dark matter, but we need to modify the Newton laws, which break at the higher distances or at the low accelerations. But this is not very welcomed in the academia. And the reason is because this theory does not explain the cosmic microwave background anisotropies. We saw in this slide, this Planck experiment, it has mapped our universe very well. And this map is based on the cosmic microwave background radiations. So this theory, this MOND, this is not in agreement with this cosmic microwave background radiations. Similarly, we have another theory for the gravity, which is the general relativity. This is a very well tested theory, but MOND, on the other hand, is not a fully relativistic theory, and it's not universally accepted theory. So this was an alternative for the dark matter, but academia usually does not consider this as a viable candidate for the explanation of dark matter. Moving on, the second explanation is the primordial black holes, and I hope you are all aware of the idea of black holes. So it is considered that the black hole could have emerged at the early universe, and the phenomena responsible for the emergence of this kind of black holes could be due to the energy fluctuations during the inflation and other things. So this is another approach to explain the dark matter, and these black holes can be in the different mass ranges. For example, uh, some black holes could have formed with the mass 10 is to power minus 11 of the solar mass. This could be possible dark matter candidates, and then there could be some solar mass primordial black holes, and even we could have some supermassive primordial black holes. So this is one viable candidate for the explanation of dark matter, and there are still studies that are studying the primordial black holes as a candidate of dark matter. Another option is the sterile neutrinos. As we saw, we already have three neutrinos in this standard model. Those three neutrinos, they participate via weak interactions. And what is the difference between the sterile neutrinos and the ordinary neutrinos in the standard model? The sterile neutrinos, they do not interact via weak force, but they only interact via gravitational effects. So that is why they are called sterile neutrinos. But because they participate in the gravitational interactions, we will have the gravitational effects that we see for the dark matter, and they can be a viable candidate for the dark matter. Their mass range can be in the kilo electron volt to giga electron volt, and they can act as a warm dark matter candidate. You will hear two words most frequently here. One is the cold dark matter, and one is the warm dark matter. So you may be wondering what is the difference between the cold dark matter and the warm dark matter. So for the cold dark matter, we assume that these particles, they have less velocities. They have some high mass and less velocities, and they move non-relativistically. But the warm dark matter or hot dark matter, these categories are for the particles that have relativistic velocities. So the sterile neutrinos, they can act as a warm dark matter candidate. But the usual uh, academia preference for the dark matter is the model that consider dark matter as a cold dark matter candidate. So the other option is the axions. These axions, they were predicted as a solution to the strong CP problem. I will not go into the details, but these can also act as a cold dark matter candidate. They are very extremely light, and they can range in between 10 raised to power minus 12 electron volt to 10 raised to power minus 2 electron volts. So these are extremely light particles, and they can also act as a cold dark matter candidate. And then finally, what we will be focusing on is the weakly interacting massive particles. So for a dark matter candidate to be a weakly interacting massive particle, it must meet the following characteristics. It must be a stable particle, it must be neutral, it must only interact via weak interactions, and it must carry some mass. Can you see why we have these four characteristics for a dark matter candidate? Of course, if a particle is not stable and it decays into further particles, then it will not exist. But we see the effects of the dark matter. So for a dark matter particle, it must be a stable particle. And why it should be neutral? Of course, again, we can understand if this particle is not neutral, this is a charged particle, then this charged particle will interact via electromagnetic or strong interactions, and we would be able to detect them easily. So that is why a dark matter candidate should be neutral candidate. And the other requirement through weak interactions, we have already seen, if it cannot interact via strong interaction, it does not interact via electromagnetic interactions, so it can only interact via weak interactions. And again, the final requirement for the dark matter candidate is that it should have some mass. So the mass, of course, if we see the gravitational effects, these gravitational effects of the dark matter can only come if it has mass. So these four characteristics, they uh, combined into this terminology that we call weakly interacting massive particle or WIMPs. So the best candidates for the cold dark matter are the WIMPs. And now we want to see if there are some kind of particles there that can fulfill this recipe, and that can be a dark matter candidate according to these characteristics. So now let's look at the standard model particle contents and see if we have particles that fulfill the previous characteristics that we were talking about. You see here we have these 6 quarks. Can these 6 quarks be dark matter candidate? No. Why? Because all these quarks, they are charged particles. And previously we saw for a dark matter candidate, it should be a neutral particle. So these 6 quarks, they cannot be dark matter candidate. Similarly, electron, muon, and tau. We have these 3 particles. These are also charged particles, so they cannot be dark matter candidate. But this last line, the electron neutrino, muon neutrino, and tau neutrino, these are neutral particles. And similarly, uh, they are stable particles, and they interact only weakly. So these 3 particles, they can be dark matter candidate, but we will see they can be a dark matter candidate, but they are not preferred dark matter candidate. So now let's move on and try to see if these 4 particles, the gluon, the photon, Z boson, or W boson, can be dark matter candidate or not. Can you guess if some of these can be a dark matter candidate? So the characteristics that we saw was it should be massive and it should be stable. So this photon, this is a massless particle. So we can rule this out. Gluon, this is also a massless particle. So this cannot be a dark matter candidate. But this Z and W boson. Okay, this W boson, this is a charged particle. So this cannot be dark matter candidate. What about this Z boson? Can this be a dark matter candidate? Or even what about this Higgs? Can this be a dark matter candidate? Again, no. And the problem is this Z boson and Higgs boson, they are not stable particles. They decay into further particles. So that is why they cannot be dark matter candidates. So among all these standard model particles, we are left with only the electron neutrino, muon neutrino, and tau neutrino. But these 3 particles, they can be dark matter candidate, but their masses are so small that they can only form fraction of total required relic density. So even though they can be dark matter candidate, but they can only 1 or 2% of the total dark matter. So we will need more particles that can act as a dark matter candidate. So if there is no particle in the standard model, what we can do? We can look for the physics beyond the standard model and propose some new models that can act as a dark matter candidate. And supersymmetric models or supersymmetry is one of the most viable candidate and most studied extension of the standard model that is there. Now let's see what is supersymmetry. Supersymmetry is a theoretical framework that extend standard model of the particle physics, and it proposes new particles. For example, for every standard model particles, we have this neutrino, photon, quarks, electron. Supersymmetry proposes that there are other particles that are similar to these particles but differ in one characteristics, and that one characteristic is the spin. For example, if the neutrinos they have spin half, there will be supersymmetric neutrinos that we call s neutrino, and they will have spin 0. So they will have more mass than the neutrinos. Similarly, if we have a photon, supersymmetry predicts that there will be another particle that will be similar to photon, with one exception, that it will have actually two exceptions. It will have different spin and more mass compared to the photon. So photon is a massless particle, but photino will have some mass and it will be spin half particle. Then supersymmetry predicts that for every quark and every lepton, there will be as quark, supersymmetric quark, and supersymmetric leptons. So this supersymmetry is a very beautiful theory, and this does not only solve the dark matter problem, but there are other problems in the standard model that are beautifully solved by the supersymmetry. So now let's look at the particle spectrum of the supersymmetry. So in the standard model, as I talked earlier, we have these quarks, and supersymmetry predicts that we will have the scalar quarks. Similarly, for the leptons, we will have scalar leptons, and for the gauge particles, for example, photon, gluon, Z boson, and W boson, we will have supersymmetric particles like photino, gluino, xeno, and vino. And in the supersymmetry, we have five physical Higgs bosons and their corresponding supersymmetric particles. So this is the particle spectrum of the supersymmetry, and the beauty of this theory is that it solves many standard model problems. For example, as I talked earlier, supersymmetry beautifully solves the Higgs mass hierarchy problem. I'm not sure if you remember this problem that I talked earlier, but the standard model predicts that the Higgs boson mass should be infinite. But what supersymmetry does is it introduces some extra particles in the equations, and those extra particles they cancel the infinities in the equations, and then we get the finite Higgs boson mass for the supersymmetry. Similarly, when we introduce the supersymmetric particles, the forces they unify at a single point. Here you can see the gauge couplings, they are a function of the energy. And for example, if you look at the present scale, which is something like this is the electroweak scale, which is 100 around 100 GeV or so. The three gauge couplings, their strength is different. But if we extrapolate these couplings, they meet at about 10 to the power 15. This scale, this is called the grand unification scale. And if we only have the standard model particle spectrum, these couplings, they meet at with each other, but they do not meet at a single point. But when we introduce the supersymmetry, then what we see is these three gauge couplings, they meet at a single point. So this is the beauty of the supersymmetric theories, that they predict the gauge unification in a beautiful manner. So along this beautiful explanation of the gauge coupling, supersymmetry also provides us with a dark matter candidate. For example, as I said earlier, we have five physical Higgs bosons and their corresponding Higgs zenos. Higgs zenos are the supersymmetric particles of the Higgs bosons. Similarly, we have the gauge supersymmetric particle of the gauge bosons that are called gauginos. And from these particles, the neutral components, if you remember, we said that for a dark matter candidate, it must be neutral, it must be stable, and it must be weakly interacting. So all these characteristics can be obtained by the neutral component of these particles. For example, this photino, this hexenos, and this xeno. They can form new states of particles that are called neutralinos. And the lightest of these neutralino can be a dark matter candidate. So supersymmetry beautifully provides us with the existence of dark matter. And now just to give you a flavor how this existence is studied in the literature. So, in this paper, we have looked at the existence of this cold dark matter candidate, that is the neutralino, and tried to see if we can obtain the Rayleigh density in the range that was predicted by that was measured in the Planck experiment that I showed earlier. So, I'll not try to explain these plots, but just to give you the flavor what is going on in the academia. So the neutralino can be a good dark matter candidate. So that's it. Thanks for your time. And if there are questions, I would be happy to answer.
Thank you, Dr. Rehman, for such an enlightening talk on the mysteries of dark matter. We now invite the participants to share their questions. The floor is officially open for discussion.
So the participants can either write their question in the chat, and I've also tried to allow them to unmute themselves. So meanwhile, participants think of any question they want to ask. I would like to ask Dr. Rahman that, as you started the talk with the standard model, and we know that it is the work of Abdul Salam, who, belonged to Pakistan. And since I know that you have also made some YouTube videos uh, emphasizing the importance of Abdul Salam. So I would just request you to, say a few words about, why you think Abdul Salam's work is important, and, Pakistan should be proud of, you know, uh,
No doubt. I mean, we have only one Nobel laureate, so we should be proud of this work. Actually, the work is very important because I think Dr. Salam's 1958 paper. Most of the when we talk about this standard model and the work in the standard model, most of the people think that it was the 1964 paper or 1967 paper that acted as a precursor to the standard model. But when I was making these videos and doing some research, I was very much fascinated by the basic ideas that was present there in the 1958 paper. So the main thing that happened in the 1957, there was this discovery of the parity violation, and this Mam Lee and these people they uh, in, proved that there is parity violation in the weak interactions. So in the 1958 paper, Dr. Abdus Salam, they have incorporated this parity violation and this chirality structure very beautifully in the weak interactions. So that was the precursor to this whole theory. And then based on this paper, Glashow then took the work from there and then introduced the group structure that we now see as the SU2 cross U1 structure. And then in 1964, Dr. Abdus Salam again uh, improved the work of Glashow and modified this whole theory. And then in this same period, the Higgs mechanism appeared just a few miles away. Both Higgs, they were also there at the Imperial College, I think, and then Dr. Abdus Salam was also working there. So that was a very beautiful era, and many things were happening at that time and at the that era. So using this Higgs mechanism, then Weinberg he modified this work of Abdus Salam and Glashow and presented a very unified theory. So, of course, being a particle physicist, I'm very much fascinated by the work of Dr. Abdus Salam, Glashow, and Weinberg. And for me, this is also very important because my teacher, Dr. Kamaluddin Ahmad, perhaps you know him. So he was a student at that time at the Imperial College, and everything that was happening, he was the eyewitness of this phenomena. And he used to share many fascinating stories about this development and all that thing. So, no doubt, we are very proud of the work that was being done there.
Thank you. Thank you. So anybody can ask if there's any question. And somebody asked, so if you are comfortable in asking in Urdu, so I think most of the audience is like, we don't have any international participant today, so you can ask in Urdu also.
या इफ यू वांट, अगर आपको उर्दू में क्वेश्चंस करना है तो मोस्ट वेलकम, हम उर्दू में डिस्कशन कर सकते हैं.
So we also have shared a feedback form in chat. So all the participants are requested to fill that up also. It will help us improve our future webinars.
अस्सलाम वालेकुम सर.
वालेकुम अस्सलाम.
सर मेरी आवाज़ आ रही है आपको?
जी जी.
अच्छा सर, मेरा एक ये सवाल है कि इसको डार्क मैटर ही क्यों कहते हैं, मतलब इसकी बिहाइंड क्या रीज़न है? और दूसरा आपने बात की कि मतलब ब्लैक होल जो है वो मतलब इसकी वजह से जो है डार्क मैटर जो है वो जनरेट होता है, तो मतलब ब्लैक होल जो है वो किस तरह कंट्रीब्यूट करता है डार्क मैटर में?
ओके, गुड क्वेश्चंस. पहले तो ये कि इसको हम डार्क मैटर क्यों कहते हैं, वो इसलिए क्योंकि अगर तो ये मैटर विजिबल होता, जिसको हम अपनी आंखों से देख सकते हैं, तो फिर हमें उसका ऑलरेडी पता होता है और हमने उनके इफेक्ट्स को ऑलरेडी अपनी इक्वेशंस में शामिल कर चुके होते हैं. लेकिन इसको हम अभी तक अपने जो इंस्ट्रूमेंट्स हैं, अपनी टेलीस्कोप्स हैं या इस तरह की चीजें हैं, उनके थ्रू हमने इसको नहीं जाना. बल्कि हमें ये पता है कि यूनिवर्स में कोई चीज एग्जिस्ट करती है, लेकिन हम उसको देख नहीं पा रहे. तो इसलिए हमने उसको नाम डार्क मैटर का दे दिया. बाय द वे, लाजमी नहीं है कि उसको डार्क मैटर ही कहा जाता, उसको कोई भी नाम दे सकते थे, लेकिन चूंकि उसको हम देख नहीं पा रहे थे, इसलिए हमने उसको डार्क मैटर का नाम दिया. जहां तक आपके दूसरे क्वेश्चन का ताल्लुक है, तो ब्लैक होल्स के बारे में मैंने ये कहा था कि ये एक ऑप्शन है जिसके थ्रू हम इसको एक्सप्लेन कर सकते हैं. हमने 5 से 6 ऑप्शन देखे थे कि हम डार्क मैटर को किस तरह एक्सप्लेन कर सकते हैं, तो ब्लैक होल सिर्फ उनमें से एक है. तो जब प्राइमोर्डियल ब्लैक होल्स की अगर बात करें, तो प्राइमोर्डियल का मतलब ये है कि जब हमारी यूनिवर्स बन रही थी, जब ये कायनात बन रही थी, तो उसके बहुत ही आगाज में, बहुत ही यानी कि आप ये समझ लें कि बिग बैंग के फौरन बाद ये प्राइमोर्डियल ब्लैक होल्स हो सकता है कि बन गए हो. हम अभी यकीन से नहीं कह सकते कि वो वाकई बने होंगे कि नहीं, लेकिन एक हाइपोथेसिस है, एक मफरूजा ये है कि हो सकता है कि इस तरह के ये ब्लैक होल्स बन गए हो, जो कि फिर डार्क मैटर के तौर पे जिन्होंने एक्ट किया, और वो जो है वो फिर लार्ज स्केल स्ट्रक्चर को, यूनिवर्स को क्रिएट करने का बायस बने. सो दिस इज वन, जस्ट वन ऑप्शन. So I'm not sure if I answered your question properly.
हेलो, अस्सलाम वालेकुम.
वालेकुम अस्सलाम.
जी सर, मेरा सवाल ये है कि इन केस हम डार्क मैटर और डार्क एनर्जी को समझ पाए कंप्लीट सही तरह, तो क्या ये साइंस में क्या इनकलाब ला सकते हैं, मतलब क्या चीज चेंज हो सकती है, क्या फर्क पड़ सकता है साइंस के जो जितनी भी हमारे पास फील्ड्स हैं उस पर क्या फर्क पड़ सकता है?
देखिए, ये जो सवालात हैं, जैसे कि ये आपको पूरी एक लिस्ट नजर आ रही है, तो ये हमारी बेसिक अंडरस्टैंडिंग्स को इम्प्रूव करते हैं. तो इसमें मैं ये तो नहीं कह सकता कि इससे ये फ्लैट टेक्नोलॉजिकल इनकलाब आ जाएगा या ये चीज रेवोल्यूशनाइज हो जाएगी, लेकिन जो हमारी बेसिक अंडरस्टैंडिंग है वो बहुत इम्प्रूव हो जाती है। और जो हमारे एग्जिस्टेंस के फंडामेंटल क्वेश्चंस हैं कि हमारी यूनिवर्स कैसे बनी और वो कौन कौन से मराहल थे जिनके थ्रू बनी, तो उनको हमारी अंडरस्टैंडिंग में बहुत इम्प्रूवमेंट आती है। और फॉर एग्जांपल अगर हम डार्क मैटर को अंडरस्टैंड करते हैं, तो जो कायनात का जो प्रेजेंट मॉडल है कि ये यूनिवर्स कैसे बनी, जिसको हम लैम्डा सीडीएम मॉडल कहते हैं, लैम्डा सीडीएम में ये सीडीएम का वर्ड ही कोल्ड डार्क मैटर है। तो वो सारा का सारा मॉडल जो है वो डार्क मैटर की एग्जिस्टेंस के ऊपर रिलाई करता है। तो अगर हमें ये पता चल जाता है कि वो डार्क मैटर किस तरह के पार्टिकल्स से मिलके बना है या क्या चीज है, तो फिर उससे हमारा जो ये यूनिवर्स की एग्जिस्टेंस का नॉलेज है वो बहुत ज्यादा इंप्रूव हो जाएगा। एंड सेम गोज फॉर द डार्क एनर्जी, कि वहां पे भी अगर हमें पता चलता है कि डार्क एनर्जी की फॉर्म क्या है, तो फिर हमें जो बेसिक अंडरस्टैंडिंग है उसमें काफी इंप्रूवमेंट आएगी। Okay,
We
I
have a
think there is,
question in the chat box.
yes. Does dark matter produce gravitational waves like simple or visible matter? So, actually, I'm curious to know, can we detect or prove the existence of dark matter by gravitational waves or in the future? Okay, this is a good question. तो जो हम डार्क मैटर की मैपिंग करते हैं, जैसे कि हमने अगर मैं इस स्लाइड पे जाऊं, तो ये जो पूरा मैप है जहां से हमने डार्क मैटर की रैलिक डेंसिटी, मेरी स्लाइड विजिबल है ना?
जी सर, बिल्कुल।
हाँ। तो ये जो हमने डार्क मैटर की रैलिक डेंसिटी क्या एस्टिमेट किया है, ये सारे ये ग्रेविटेशनल इफेक्ट्स और वेव्स और इन सब को इनकॉर्पोरेट करके किया है। तो ग्रेविटेशनल इफेक्ट्स तो है डार्क मैटर के, लेकिन अगर आपका एग्जैक्ट क्वेश्चन ये है कि वो ग्रेविटेशनल वेव्स की फॉर्म में, तो ग्रेविटेशनल वेव्स आपको पता है कि अभी तक हम जो डिटेक्ट करते हैं वो बहुत ज्यादा स्ट्रॉन्ग ग्रेविटेशनल इफेक्ट्स की वजह से जो वेव्स प्रोड्यूस होती हैं, फिर जाके हम कहीं उनको डिटेक्ट कर पाते हैं। तो डार्क मैटर के लिए हमारे पास जो ग्रेविटेशनल इफेक्ट्स हैं वो इतने ज्यादा स्ट्रॉन्ग नहीं है। ऑफ कोर्स देयर विल बी ग्रेविटेशनल वेव्स, लेकिन वो इतनी ज्यादा स्ट्रॉन्ग नहीं है कि उनको हम अपनी प्रेजेंट टेक्नोलॉजी से डिटेक्ट कर सकें। लेकिन इसका मतलब ये नहीं है कि हम डार्क मैटर को डिटेक्ट नहीं कर सकते। उसके लिए हमने डिफरेंट एक्सपेरिमेंट्स लगाए हैं और उनकी डिटेक्शन के ऊपर काम जारी है। जैसे ये जो लास्ट स्लाइड थी, इसमें अगर आप देखें, तो ये तीन एक्सपेरिमेंट्स आपको नजर आ रहे होंगे। इसमें से एक एक्सपेरिमेंट को जीनॉन कहा जाता है, दूसरा एक्सपेरिमेंट इज कॉल्ड लक्स, एंड थर्ड एक्सपेरिमेंट इज कॉल्ड डार्विन। तो अब ये जो प्लॉट थोड़ा सा हमें ये बता रहा है, ये जो ऑरेंज लाइन है ये डार्क मैटर डिटेक्शन की लाइन है। और यहाँ से मतलब ये एक्सपेरिमेंट्स हमें बताते हैं कि डार्क मैटर किस नेचर का है और उसको किस तरह डिटेक्ट किया जा सकता है। तो वी कैन नॉट सी द इफेक्ट्स ऑफ डार्क मैटर इन टर्म्स ऑफ ग्रेविटेशनल वेव्स, लेकिन हमारे पास दूसरे डायरेक्ट डिटेक्शन और इनडायरेक्ट डिटेक्शन एक्सपेरिमेंट्स एग्जिस्ट करते हैं, जिससे हम डार्क मैटर की एग्जिस्टेंस का अंदाजा लगाते हैं। Okay, any other question?
I
So I
don't think
guess
we
there
have any other questions.
क्वेश्चन है सर। जी जी।
जी प्लीज।
अच्छा सर, ये क्वेश्चन है कि ये जो मसनूई सियारे हैं, तो क्या ये डार्क मैटर और डार्क एनर्जी का मुशाहिदा कर सकते हैं? मतलब उनमें कुछ चीजें डिटेक्ट कर सकते हैं या इस तरह कुछ हो सकते हैं?
देखिए, ये मसनूई सियारे तो हम डिफरेंट पर्पसेस के लिए बनाते हैं ना। अब जैसे हमने ये मैं पहले भी दिखा रहा था, ये जो प्लैंक ऑब्जर्वेटरी है, अ, ये आपको एक एक्सपेरिमेंट नजर आ रहा है। तो ये हमने स्पेस में ये प्लैंक एक्सपेरिमेंट जो है, ये अपनी एक आप यही समझिए, हमने ये मसनूई स्यारा भेजा हुआ है। तो ये यही काम करता है। ये इसका काम ही ये है कि उसने पूरी यूनिवर्स में जहां जहां पे डार्क मैटर और डार्क एनर्जी है और कितनी है, उसका अंदाजा लगाना है। तो यस, मतलब सारे मसनूई स्यारे ये काम नहीं करते। हर मसनूई स्यारे का अपना अपना एक पर्पस होता है। लेकिन ये प्लैंक एक्सपेरिमेंट है, ये एक मसनूई स्यारा है जो हमने खला में भेजा था। इससे पहले एक डब्ल्यू मैप था। तो हमने इस तरह के एक्सपेरिमेंट्स डिजाइन किए हैं जो खला में जाके डार्क मैटर और डार्क एनर्जी के ऊपर रिसर्च कर रहे हैं।
All right, sir. It was I think, a very good discussion और बड़े अच्छे सवाल है, and we are very happy कि participants ने interest लिया. So I think we can end it. So Hafsa, I think you can conclude.
Yes, thank you,
Yeah.
Imran. Thank you so much, Dr. Rehman, for answering all the questions. And for the participants, as Mr. Imran said, please take a moment to fill out our feedback form. And also you can follow us on Facebook for updates on upcoming webinars. Thank you so much, everyone.
Thank you. Bye.
So I would request our co-host to stop the recording.